said earlier this morning, in these times where everything is a bit upside down, it's important that we understand, we recall that research is still a very important part of what we do and what the board represents. So today we decided that we would have 4 of our board members share with you a bit about what they do in their research. And we have I think a nice lineup of 4 talks that will be about 20 minutes or so each. And there'll be plenty of time for questions afterward. And we hope that you enjoy the morning or afternoon for many of you. So with that, I'm gonna pass it over to Elizabeth and have her welcome you on the account of the Academy, as well as give us some background as to what will go on in the next few hours. And I suppose one final thing that I didn't do was to introduce myself. I'm Isabel Montañez. I am the chair of the board. Elizabeth.
Thank you very much, Isabel. And welcome everyone. Good morning, good afternoon, whatever your time zone happens to be. We're really pleased that you're all able to join us here today. And it's wonderful to see all of you. We would love to have seen you in person, but of course, the Zoom option gives us some advantage in being able to be together today. And we are really excited about this virtual spring meeting of BESR. The program, we started first discussing this back when things were starting to move to telework situations. And we wanted, as Isabel said, to move from our in-person meeting to this virtual one. And we wanted to use the shift as a real opportunity to highlight not only important and interesting Earth science research, but also give a glimpse into the many talents and deep knowledge base represented by our board members, 4 of whom kindly agreed to help us today by providing some talks about the research in which they're involved. So we're really excited about the program and happy that all of you could join us. Before I get into some of the logistics for our meeting, and we'll do a quick round of introductions of the board members, I wanted to be sure to offer my sincere thanks to Deb Glickson, Eric Edkin, and Courtney Devane from our staff team, and our 4 board members who are speaking today, Isabel, Michael, Bill, and Estella, for their great contributions in setting up the whole program. So I wanted to do a couple of technical items for you here before we get underway, just to make sure that we take advantage as much as possible of the interactive features of Zoom. So I wanted to review the agenda for you and how you can provide questions for our speakers. We really want to make this as interactive as the medium can allow. So all 4 of our speakers are each going to talk for about 20 minutes, after which we'll have roughly 10 minutes for discussion specifically related to that presentation. We'll also have time set aside at the end of today's session, about 20 additional minutes or so, for further questions and discussion that could be related to any of the talks or about the board's activities more broadly, just as a general plenary for the day today. And so to avoid background noises, we're going to keep everyone muted during the presentations. And to ask questions, you see Eric has up here on the screen the instructions for you. I think many of you are very, very familiar by now with Zoom features, but we'd like you to use the raise hand feature for all comments or questions, and the host will unmute your microphone once you're called on. So I'll be moderating Isabel's talk and the questions there, and then Isabel will moderate the rest of the day, and we'll be looking for the blue hands to be raised. If you don't want to interject your question with your own voice, you can also post comments by using the chat function and posting the message to everyone. Deb and I will be monitoring that chat function, and we'll make sure that those questions are raised during the course of the Q&A session. And we just ask you to reserve your messages for the meeting as they relate to the meeting topic. If you have a specific technical question, you can reach out in a specific email or a specific chat function to Eric Edkin. So Eric is running the technical side of our program today. If you have technical issues, please do reach out directly to Eric with that. Finally, I wanted to mention to you that this session is being recorded, and we'd like to post the recording on our website probably about 7 to 10 days after the meeting. And we're grateful for our speakers for their contributions. With that said, I wanted to do a quick round of introductions, allow the board members to say hello, their names and affiliations, and then I'll get going with the introduction for Isabel and allow her to get underway. So I think I see people see themselves off to the right to try to keep this in a coordinated way. Maybe I'll just call on you, our board members, and then have you, Eric can unmute you, and then we can get underway. So I think I see Brenda, you're first up on the list. Please go ahead.
Good morning, everyone. I'm Brenda Bowen. I'm a geology professor at the University of Utah and director of the Global Change and Sustainability Center here, and happy to be a part of BESR in this meeting. Look forward to learning a lot today.
Thank you, Brenda. Carol?
Hi, Carol Harden. I'm a professor emerita of the University of Tennessee, although I reside in Vermont. I'm a geomorphologist, and I'm looking forward to hearing about something that, topics that we haven't had in the news recently.
Terrific. And we are too, Carol. Scott?
Scott Cameron. I'm a petroleum geology consultant, and I live in coastal Washington State. Glad to see you all, and looking forward to today's presentations.
Thanks, Scott. Elizabeth?
Hi, Elizabeth Wilson. I'm a professor at Dartmouth College and currently in Copenhagen. If anyone wants to talk about life in a place where it's sane.
You are very fortunate, Elizabeth. Glad that you're safely over there. Estella, please.
Hi, Estella Atekwana from the University of Delaware, currently serving as the Dean of the College of Earth, Ocean, and Environment. And my background is in near surface geophysics as well as deep crustal geophysics.
Excellent, thank you, Estella. And we'll hear from you later today too. Jim?
I was muted, sorry. Jim Slutz with the National Petroleum Council. And let me just do a quick advertisement for Wednesday is the Committee on Earth Resources meeting. And we are doing a couple-hour session on carbon capture, use, and storage. We have a great lineup of speakers, and it begins at 11 a.m. Eastern. I think everybody received the information on it, and so hope you can join us, the committee, on Wednesday.
Thanks a lot, Jim. And if you don't have information but would like some about that meeting, please feel free to reach out to me separately by email or in the chat function. Jeff, please.
Morning, Jeff Rubin, semi-retired emergency manager and geologist, currently unsemi-retired, working on our state's COVID-19 response in Oregon.
Great, thanks for all that work for the cause, Jeff. Michael.
Am I unmuted now? Michael Manga, I'm at the University of California, Berkeley.
Thanks, Michael. Look forward to hearing from you later. Bob?
Right. Following 40 years of technology development in the oil and gas industry, I'm now affiliated with Columbia University and Boston University, working in energy policy units.
Thanks a lot, Bob. Rod Ewing?
Good morning. I'm a professor at Stanford and co-director of the Center for International Security and Cooperation. Main focus of my work has to do with minerals, material science, and in particular, nuclear materials.
Thanks a lot, Rob. Good to have you with us. Bill Hammond?
Hello, I'm Bill Hammond. I'm a professor at the University of Nevada, Reno, coming to you from my bedroom.
Thanks, Bill. Look forward to hearing your talk later today as well. So I think, Isabel, with that said, I'm going to.
We forgot Shawan.
Oh, I didn't see Shawan on here. There he is.
Yep.
Thank you. Thank you very much. I didn't see him. Shawan, I apologize. Go ahead.
Hello, everyone. This is Xiaowen Wang. I'm a professor and head of the Department of Geography and the Geographic Information Science at the University of Illinois at Urbana-Champaign. Great seeing everyone virtually, but very animated and smiling faces.
Thanks, Shawan. Just before I close, I'm trying to keep track here. Did I miss anybody else from the board? And if so, I apologize.
Did we do Nelia?
Why is Nelia not? I'm not seeing Nelia on the list of the BESR. Nelia, go ahead.
There she is.
There she is. Nelia, are you there?
Yes, I'm here.
There you are.
Good morning. My name is Nelia Dunbar, and I am the director of the New Mexico Bureau of Geology and Mineral Resources and the state geologist of New Mexico. I'm a geochemist and igneous petrologist by training, and it's great to see everyone, and I'm really looking forward to the talks this morning.
Excellent. Thank you, Nelia. Anybody else, Isabel?
I think that's it.
That is it. Okay. So I will turn the floor back over to you in a moment. For those of you who aren't aware, Isabel, of course, is our board chair, but she's also the University Distinguished Professor and Chancellor's Leadership Professor in the Department of Earth and Planetary Sciences at the University of California, Davis. She's a paleoclimatologist whose research focuses on geologic archives of past atmospheric gas and ocean geochemical compositions and their linkages to climate and ecosystem changes. She's a fellow of the Geological Society of America and served as president of the GSA from 2017 to 2018. And she's also a fellow of the AAAS and a geochemical fellow of the Geochemical Society and European Association of Geochemistry, and a past fellow of the John Simon Guggenheim Memorial Foundation. We're delighted to have Isabel as our chair to lead us off this morning. So Isabel, I'm just going to turn everything over to you.
Okay, great. And I think I see that I can control Eric's screen. So I feel like I'm a little bit of the guinea pig here. Let's hope this works. So my research group studies past climates, given the insight that they can reveal about future climates on regional to global scales. And over the past 15 years, we've targeted two intervals of time in particular. The first, the last glacial cycle, and let's see, last glacial cycle and deglaciation of the past few tens of thousands of years. And then the penultimate ice house of the late Paleozoic, 300 million years ago. And you may ask, why these two particular intervals? Well, they actually share a lot more in terms of similar conditions than you might think. They both had widespread continental glaciers that were susceptible to major change, or in waxing and waning. They both were characterized by low CO2 in the atmosphere, and both experienced repeated deglaciations, and in one case, a terminal deglaciation. But in the interest of time, I thought today I would talk about our work on the last 20,000 years. But before I start that, I just want to highlight why I'm very interested in paleoclimates, including these really deep times. So the importance of developing a mechanistic understanding of the Earth system under climate conditions well beyond that of our current climate state is illustrated by this diagram. And this is what we call a landscape climate stability diagram for Earth. And it shows the current position of Earth here in the back as it exits the limits of the Pleistocene glacial interglacial stability trough here in blue. And it's entering this purple to red or deepening trough of the Anthropocene. And the gray arrow shows the human-driven trajectory towards the future pathways, two potential pathways for Earth. And currently, with business as usual, the Earth system is on the trajectory towards this hothouse Earth, directing towards this planetary threshold that we consider of about 1.5 to 2 degrees. And this threshold means that after that, the Earth system follows sort of an irreversible pathway dictated by intrinsic feedbacks in the Earth system. So the time period I'm going to focus on today would be here as the last deglaciation and into our present state as we are crossing over from the stability trough of the Pleistocene into this Anthropocene trough. But I do want to point out the reason that we study the late Paleozoic or penultimate ice house is because that is the only interval we have on Earth where it was an Earth with complex marine and terrestrial ecosystems that actually passed this planetary threshold and went into a permanent deglaciation. So what you see here is the US drought index for October 2016. And in colors of yellow to red to brown are abnormally dry conditions to these extreme droughts that seized the western or southwestern US at that time. And these conditions were really part of a persistent drought that occurred in California and the West from 2012 to 2017. And this drought index indicates that other than a couple years of some wet winters, these regions, and California included, the drought conditions persist. And we know that California is no stranger to drought, including mega droughts that persisted for tens to hundreds of thousands of years. Excuse me, tens to hundreds of years or centuries. Sorry, thinking about the deep time too much. And what you're looking at here are tree stumps that are dated to the 12th and 13th centuries. And what's interesting about these tree stumps is that they are rooted. In the top picture, rooted in the Walker Creek on the eastern side of the Sierra Nevada. And on the bottom picture, rooted 35 meters below Fallen Leaf Lake, which is in the Tahoe Basin. Now, these drowned trees date back to the medieval climactic optimum or warming, and their presence suggests that the Northern Hemisphere warming could be linked to protracted drought throughout this region I'm talking about. So for us, or my group, a primary motivation for this work is to constrain the processes that have been driving past precipitation patterns in the American Southwest, including California, in order to better understand how regional hydroclimates might evolve with continued warming. So speleothems, some of you are maybe quite familiar with them. I think others may not. So what you're looking at on the left is one of our study caves and one of my graduate students, Barbara Wortham. This cave is called Lilburn Cave. It's actually a research cave run by the Cave Conservation Group. And these speleothems that form are archives of past change in regional hydroclimate, what I like to call crystallized climate. And just so everyone's on the same page, speleothems form when rainfall becomes acidified due to the soil CO2. That acidified water makes its way through fractures and porosity that's developed in the host limestone. And ultimately, when that hits the cave, it degasses. And as it degasses, it precipitates a new mineral, calcium carbonate. And these are our speleothems, stalactites from the ceiling, stalagmites from the floor. And stalagmites are archives of past drip water and thus potentially of past climate. And in particular, meaning past archives of climate as each layer develops. So speleothem-bearing caves are distributed along the western side of the Sierra in the foothills from about 36 degrees to about 41 degrees north. So this transect of caves is essentially the first orographic barrier to the northern Pacific storms that come in the winter, typically generated from the northernmost Pacific around the Aleutians, but also coming from the subtropical regions over Hawaii. And I'll say a bit more about this later. So these caves then are ideal candidates for archiving temporal change in precipitation dynamics. And what makes stalagmites, such as the one you're looking at here on the right, particularly useful is that we can date these using their uranium and thorium isotopes. to a precision of about 1 to 2% of their ages. And here on the bottom is what we call an age depth diagram. And for this particular stalagmite, that grew from 20,000 years ago, the last glacial maximum, through to about 12,000 years ago. So the beginning, just before the beginning of the Holocene, means that this particular stalagmite is capturing a continuous or near continuous record of this period called the last deglaciation. And for this stalagmite, that's with a resolution of 2 to 3 years in our proxy records. And I want to point out that a 8,000 year continuous record at that resolution is really pretty unusual, and thus the beauty of stalagmites. So we monitor, and I'm going to click on this so you can see this video. We monitor several caves in the region in order to help us better understand how the cave conditions respond to changes in regional climates. And monitoring involves both above cave and below cave conditions, such as rainfall, temperature, soil gas, cave CO2, as well as the trace element and isotopic compositions of all of the gases and waters that we monitor. And the video is showing you where we collect drip rates on a glass plate on which we are growing a modern stalagmite, basically an artificial stalagmite. And we use this stalagmite because it permits us to calibrate the geochemistry, including some challenging components of the age dating. We can calibrate these using these synthetic, essentially, stalagmites that we grow in place for each cave. And on the right, then, you see a subset of some of the monitoring data for one cave over a 5-year period. And in red is the precipitation above the cave. Below in black is the drip rate. And what I want to point out here is that both very strongly pick up the seasonal winter patterns of rain, but that they also closely correspond, meaning, and what it's showing you is that these Sierran caves respond to climate within hours to days of a particular storm. And that makes them particularly useful. Below in blue are two trends that are the oxygen isotopic compositions of the rainfall in the lighter blue, and then of the drip water in the cave below it. And again, these are picking up the seasonal oscillations in the rainfall in their isotopic compositions. But something else that's really interesting is that they can pick up these unique sources of storms. Here at the bottom, these lighter numbers are the northernmost Pacific storms being sourced from the Aleutian regions. And then the isotopically more enriched ones, in this case, are these subtropical atmospheric rivers, or what we call pineapple expresses. So this close correspondence of the isotopic compositions of rainwater and drip water means that there's minimal dampening of the precipitation signal in the cave, and thus the stalagmites have the potential to record the precipitation pattern or signal. Now I'm going to show you some time series of some data, and I don't mean for us to get bogged down on these. I really just want to speak about trends and some of the challenges and why we are developing novel proxies. So here, these are shown on a time series from oldest or last glacial maximum on the right to the beginning of the Holocene on the left. You're seeing in the color trends the oxygen isotopic compositions for 3 stalagmites. And these are not ours. They're actually from Oregon, New Mexico, and Arizona. And I want to say something about them because these have been used by many in terms of talking about teleconnections in the Earth system. At the top in black is the NGRIP ice core record, the oxygen isotopes over the same time period for comparison. And for the ice core record, values that are less negative or upward on the trend are warmer temperatures or interstadial. And when the values are down or more negative, it is the colder stadial periods. And these have been recognized in these stalagmites, and they've been given names. And so these are acronyms here at the timeline for these cold and warm periods. But what the point here is that there are these millennial scale alternations in cold and warmer periods. Overall, the stalagmite records do respond to these millennial scale warmings and coolings generally. And I'm adding here to the bottom some of our records from 2 of the caves in the Sierra. And again, these isotopic records generally respond to the stadials or interstadials. But when you compare these records, I think you can see that it's not a clear response, in that the magnitude of the changes, as well as the timing of the changes with regard to the ice core record warmings and coolings, are highly variable. And so consequently, the interpretations of these stalagmite records have been quite variable as well. Some have called on a primary driver of temperature, changes in the seasonality of precipitation, effective moisture, which by the way is the precipitation to evaporation ratio. It could mean more precipitation or greater evaporation, or both. And in our case, we have interpreted our records as being shifts in the sources of the storm tracks that come to California, as well as changes in temperature. But what I really wanted to point out with these is this variability that you see in the stalagmite records is in part reflecting that they are imprinted by multiple environmental influences, and that these influences are not easily deconvolved from one another. So in the past couple of years, or 3 years, and continuing, my group has been addressing this limitation by exploring novel and independent proxy approaches that use fossil drip water entombed in the stalagmite. So on the far left, you see an X-ray computer tomography scan, or XCT scan of a stalagmite. The pore space is the darker interval. And on the right of that is superimposed on that scan a second one, a neutron activation CT scan. And the way that this works is that neutron activation can detect water because of thermal neutron attenuation of hydrogen in the water. So on this stacked scan here, the brightest orange intervals are those that are rich in water-filled inclusions, presumably fossil drip water. And the darker intervals up here are mostly air-filled pores. So what we do is then we make stacks of these scans throughout the stalagmite and stack them to make these 3-dimensional images of, or reconstructions of, the distribution of fossil water in a stalagmite. So this is one stalagmite. In green is the fluid-rich intervals. And I want to point out these blebs of green up here. These are actually millimeter to centimeter scale pores that are actually filled with this fossil drip water. So then what this permits us to do is go out and carve in the stalagmite throughout them in little tiny millimeter-sized chips that we know are going to have fluid in them. We then have built this crushing system that actually has a catalytic converter from a motorcycle attached to it to deal with the organics in the inclusions. And we crush these chips under vacuum, and then we are able to extract the fluid and analyze them for their oxygen and hydrogen isotopic composition. So what you're looking at here is a cross plot of oxygen isotopes of waters and hydrogen on the y-axis. In the darker gray closed squares, that is the precipitation that we have gathered from our caves over the years. And in the open squares are the drip waters from some of these caves. And together, the precipitation values define this black line, or the local meteoric water line. In blue and open circles are 48 of the fluid inclusion values, or the fossil drip water, and their duplicates. And you'll see that there's quite a bit of scatter in there, and that is to be expected, one, because of the error on the analyses, but also each of those millimeter chips records anywhere from 40 to 80 years of rainfall. So given that the distribution of the inclusions are variable, you're going to see this variability. Well, what's to show on this is that the oxygen isotopic values of these are generally in line, even with the modern drip waters, but that there's a trend of the data off of the local meteoric water line. And that's really telling us that there's been a modification of these waters. This could be, for example, evaporation of the precipitation above the cave at the subcloud level, or it could be within the cave. But we can extract more information when we consider this fluid inclusion data color-coded here by discrete millennial scale climate regimes, such as in darker blue is the last glacial maximum, in yellow are the warm interstadials of the Bowling and Allerod. And for the three colder intervals, if you draw trend lines through, or regression lines through the data, it shows lines that are pretty much tracking or parallel to the local meteoric water line. But in contrast, for the warmer periods, those lines are skewed to the right. And what this suggests then is that during the warmer periods, there was lower effective moisture. Again, this can be either less rain and or more evaporation. So to investigate this a bit further, we look at these data here on a trend timeline, comparing them to the stalagmites and the ice core record. And the point I want to make here is when you look at the data, there is a trend that shows for these time periods shown by the blue arrows, that when you go from the transitions from the cold intervals into these warmer or drier intervals, cold to warm, there is a major change in the oxygen isotopic composition of these drip waters. And if you look at this one particular here at 15.1 kiloyears, you can see this is picked up in the stalagmite records as well as the northern hemisphere or Greenland ice core. And so what this is telling us is that these changes that are being recorded by the stalagmite require a major change in the precipitation dynamics between the colder stadials and the warmer interstadials. And what could this be? It could be a shift in moisture source. It could be changes in rainfall amount between warm and cold periods, or both. So in the last couple of slides, I want to speak to what we're doing to try to interrogate this bit further by looking at climate processes behind this variability in the fossil drip waters. And what we're doing is working collaboratively with assistant professors Clay Tabor from University of Connecticut and Marcus Lofestrom from the University of Arizona to carry out climate simulations for a series of time slices from the last glacial maximum through the last deglaciation and the pre-industrial for calibration. We use NCAR's CESM model. If you're not familiar with it, it's an Earth system model. It is fully coupled with the ocean, atmosphere, and land, and it has isotope water tracers. And we are currently downscaling these models to a 0.25 degree topography. So we're talking in just a few tens of kilometers, 22, 24 kilometers. So we can actually resolve the variability over the Sierra and the caves. So I'm just going to show you three sets of diagrams quickly. And so here you're looking at annual precipitation versus evaporation, or effective moisture, for the last glacial maximum at the top. And at the bottom, the diagrams are the difference between the last glacial maximum and the pre-industrial. And what this red swath then is showing you in this difference diagram that is hitting the west coast of the Americas is that there was greater precipitation in the last glacial maximum than today. When we look at the isotopic composition of the rainfall, here again at the top it's for the last glacial maximum. At the bottom, the difference between the last glacial maximum and the pre-industrial. We can see that there's a depletion of about 1.5 per mil. And this is here in this model, it is because of greater rainout of the storms as they pass over into California and into the southwest. And this can account for about half of the variability we're seeing in our drip waters. So the rest can be accounted for a little bit by temperature and a lot by the source of the moisture or the storm tracks and changes in those sources. So in our modeling, we're able to track, we call it tracking, track the moisture sources. We've tagged several places in the Pacific as well as in the Caribbean and even in the Atlantic. And we can see where molecules of water are coming in these storm tracks as they hit California and the Southwest. At the top, this is on the left is for the last glacial maximum. On the right is the difference, last glacial maximum pre-industrial. And the top are for extratropical cyclones coming in, hitting the western coast of North America. In the difference diagram, you can see that there are more extratropical cyclones during the last glacial maximum. But I think the one that's really interesting is at the bottom here. This is for also extratropical cyclones, but specifically atmospheric rivers. And these are subtropical moisture sources coming in over Hawaii, like a fire hose hitting the coast. This is the last glacial maximum. The difference diagram then suggesting that these two were contributing extra moisture during the last glacial maximum versus today. And this is one of the atmospheric rivers caught in or revealed by our modeling and hitting the coast of California, moving in southwards. Okay, so I'm going to leave it at that. I'll just say that to wrap up, that we've spoken today. This work is very much one of a work of progress. Our future work aims to develop spatially resolved stalagmite proxy records throughout California, and that we want to continue our data model comparisons through multiple time slices of the last glacial cycle and deglaciation, with the ultimate goal to get a holistic perspective of what drives precipitation patterns in the US Southwest under changing climates. Thank you. And I did not track my time as I had planned to, so hopefully Elizabeth did, and I'm hoping I have time for questions.
Yes, you didn't feel me nudging you under the table, Isabel? No, I'm just kidding.
You didn't. Yeah, I had my watch ready to track time, and did I push the button? No.
No, you're absolutely fine. That was great. Thanks for such a stimulating presentation. And we'll open the floor now to questions that people may have. Again, if you want to use that the blue hand function to raise your hand to ask Isabel a question, and while you're getting your questions lined up, maybe I'll take the moderator's prerogative and start things off. So Isabel, really, really neat to see the way you're taking the detail from the stalagmites and combining it in different ways to look at these larger scale models. I wonder if you could talk toward this challenge. You were talking about downscaling from the Earth system models, and I know that's just a big challenge overall with folks working on climate issues in paleoclimate. I wonder if you could talk about how your work and how you're concentrating on trying to use this field data, which is at a very, very fine scale, and then looking at these regional and in fact global Earth system models. What are the big challenges that you see in trying to move those all into an even better place where the models can be even more precise down to levels that would make sense at the regions where you're doing your work? What are the big challenges that you see there?
So you're absolutely right. I mean, climate change. One of the reasons that this kind of work intrigues me is that climate change or hydroclimate is at the regional scale. That's what affects people. So we have to understand at the regional scale. And I will tell you, before I answer your question specifically, that our ultimate goal is to take this downscaling and be able to interface it with a single drainage basin water model. I mean, we would love to be able to ultimately say something about surface and subsurface water. So we are absolutely, Clay Tabor, who is the one who's doing the downscaling, and that is of the two modelers, the one has the most experience in that. And there's no question, we are constantly running into challenges. But what we have seen is very promising. We can, because the model actually will model the water within the soils. We can't get to individual caves, but we can get to clusters. So southern, central, northern cave systems. And our records are showing very distinct differences in those regions, as well as with elevation. So the challenge is going to be elevation. We're not doing that real well. But in terms of spatially, within the Sierra, the three main regions of south, central, and northern for the foothills or the west side of the Sierras, it's promising. And the absolute isotopic values in oxygen are actually matching. The hydrogen's a different story. But this is really very promising to us, that we can not only get the trends in the model, but we can actually see the isotopic values overlie one another. And that we didn't expect, and at these scales, and resolve the differences, not just in the time slices, but also spatially. So we absolutely have challenges. We're looking at about a 20-kilometer grid. We wouldn't certainly go any further than that, but what we're hoping then is if we can, and we have a good year before we can actually say this with full confidence. I mean, we're writing our first climate modeling paper right now, but I think we're hoping that given what we're seeing, we can actually then start doing some data assimilation where we can actually quantitatively compare the proxies for those regions and the downscaled grids, and that will be the true moment of truth, right? Whether we're succeeding or not. So I think there's a lot of promise in so many short words.
Thank you very much, Isabel. I see that Scott has his hand up, and I think in order to stay on time, we'll make Scott the last question for this round, but we will have time at the end of today's session if you have additional questions for Isabel or others. So Scott, please go ahead.
Isabel, that was a great talk, and looks like you have a pretty spectacular data set from the caves in California. I'm wondering if potential exists to extend that data set up into further to the north, into the Oregon, up through into British Columbia to see the regional variations of the, that you were seeing the two sources for the moisture.
Yeah.
I'm wondering if you can calibrate that further to the north with similar kinds of cave deposits on a more regional scale.
So, you're absolutely, I couldn't agree with you more. I would say one of the biggest challenges in working with speleothems is actually access. And our California caves are primarily owned privately and by just a handful of people they're in the parks, either a state demonstration forests or national parks. And that's a real challenge. I tried to get into British Columbia quite a few years ago with one of the California cave owners who had access, and that fell through. Oregon is sort of established territory of some other people. So it's a bit of this negotiating. There's an awful lot of negotiations that go along, and calls and pleading and visits, but I would love to. And so if you have any contacts or if you come across them, please, I would, you're absolutely right. That is the next step. Because you cross a climate dipole there in Northern California, Oregon. So you should see a reversal, and it would be really interesting. Mm-hmm.
One quick question. Are all the caves in the same geologic formation?
So in California, yes, but they are not, we don't know, because these are accreted marble terrains. They were probably carbonate platforms around as atolls, and then were accreted onto the Sierra, and we think they're permacarboniferous, and the pods are about 60 meters, 100 meters, kilometers in size, kind of thing.
Those terrains extend all the way up into British Columbia, but kind of a circuitous route from the Klamaths to the Blue Mountains, up into the North Cascades, and then up. So there might be potential. That's okay. Thanks very much.
Yeah, well, keep your ears open. I'd be
I'll do that.
Very open to that. Thank you.
Great. Thank you very much, Scott. And thank you again so much, Isabel. I will turn the floor back over to you, Isabel, if you would, to introduce our next speaker.
Yep. Let me pull up my cheat sheet quickly. Okay, it's my pleasure to introduce Michael Manga. He is a professor and chair of the Department of Earth and Planetary Sciences at UC Berkeley. Michael has a large portfolio of research experience and interests. Much of it is focused on understanding volcanic processes from the deep subsurface to eruptions at the surface and their impacts. His work has taken him around the world as well as to other planets. And his work is very well recognized internationally. It's been recognized by quite a few awards, including the GSA Donas Medal, the AGU's McElwain Medal, and a MacArthur Fellowship. And I think it's worth pointing out that even with by the first UC Berkeley Distinguished Teaching Award, and there's not many excellent researchers that excel there as well. So with that, I hand the screen over to Michael to talk about submarine volcanic eruptions.
Excellent. If you put simple questions in the chat box, I'll see if I can pay attention and I can try and address them real time. Also, happy belated Mother's Day. So one of the key questions in volcano science is understanding why volcanoes erupt in so many ways. For example, in 1980, Mount St. Helens erupted explosively, sending ash high into the atmosphere, and it was distributed over a broad area. In 2004, Mount St. Helens also erupted, essentially the same magma, but in a style we call effusive to make the slab a dome. And we understand the basic processes that make volcanoes erupt. Magma at depth contains dissolved volatiles, mostly water, but CO2 and other gases as well. As this magma rises, the pressure decreases. Eventually, the melt becomes saturated with respect to those volatiles. Bubbles come out of solution. Bubbles grow from the gases that come out of solution. And eventually, the magma can fragment. And fragmentation is an important process. We go from a continuous melt phase to now having discrete pieces of bubbly magma surrounded by a continuous gas phase. And it's those fragments that can erupt explosively. So what we're going to do today now is look at eruptions that occur under the sea, both how they erupt and then why they erupt the ways they do. On July 18, 2012, the Havre Submarine volcano in the Kermadec Arc, north of New Zealand, erupted more than 1 cubic kilometer of pumice, creating a raft of floating rock. And over the coming years, this pumice was transported throughout the southern oceans, washing up on beaches. Now, I can't pass around a rock, but I can show one maybe in my screen. Hopefully you can see this. And it's nicely rounded. This washed up onto the shore and shores of New Zealand. And it's rounded because these pieces of pumice abraded against each other, getting rounded during transport. And since you can't see it, you don't get a sense of its density, but I can put it in this cup of water and you can see that it floats. And that piece of pumice would float for many years. Okay. Now, amazingly, scientists didn't know about this eruption until 2 weeks later, when a passenger in a commercial airplane saw the raft of floating pumice and contacted a volcanologist in Australia. Now, in fact, most submarine eruptions are discovered by serendipity. The plot on the left shows the cumulative number of eruptions in the Smithsonian database over the last several decades, and this amounts to knowing about or detecting less than 1 eruption per year. For comparison, about 100 different erupt on land every year, and given that 85% of magmatic volcanism occurs in the oceans, we're probably aware of and documenting 1 in 1,000 eruptions under the sea, despite all the modern tools we have at our disposal to monitor the Earth. The 2017 National Academy Volcanic Eruptions, Their Repose, Unrest, Precursors, and Timing report highlighted as one of the 2 grand challenges in volcano science, to quantify the life cycles of volcanoes globally, to overcome our biased understanding. And eruptions under the sea are poorly documented, their life cycles and the processes that control their eruptions, as well as the fate of erupted materials, remains poorly understood. The map on the left shows the dispersal of this raft over the first several weeks, with colors showing the location of the raft at different times. In brown is the position of the raft one day after the eruption, and even then, the raft covered 400 square kilometers of the ocean. And these rafts are more than curiosities. They can be colonized by life and then transport that life great distances. And as the pumice floats, it abrades as the pieces rub against each other, and this releases ash and nutrients into the ocean, fertilizing the ocean. Well, there are several questions about this eruption and submarine eruptions more generally. How much erupted, and what was the eruption rate? We will see eruption rate has a primary control on how it is that magma erupts. What do the deposits from these eruptions look like? Answering this question will help us interpret the geological record. How is it that the magma erupted? And how did it get from almost a kilometer below the ocean surface up to the surface of the ocean? And the challenge to answering all of these questions is that really all we had was an observation of the position and shape of the raft from satellite images. So in March 2015, the MESH expedition sampled and mapped the Havre volcano, where MESH is an acronym for Mapping, Exploration, and Sampling at Havre. There are two main components. First, the remotely operated vehicle JASON collected samples and recorded lots of video. And the autonomous underwater vehicle Sentry mapped 56 square kilometers of the seafloor at better than meter scale spatial resolution. Now, leading up to the cruise, we expected to see a pile of pumice accumulating on the seafloor that was fed by the raft we saw at the surface. In fact, the high resolution bathymetric map revealed that 14 new lava flows and domes erupted, labeled and colored A through P here, with a volume that amounts to about 0.3 cubic kilometers. One distinctive feature of this eruption is a field of large pieces of pumice we call giant pumice, some pictures down here at the bottom, that have diameters that exceed 1 meter. The background image that you see here is the bathymetric map, and even in the bathymetry, you can see these giant pieces of pumice, and they can get quite big. And I guess I should point out that equivalent eruptions on land do not erupt pieces of pumice that are this big. These giant pieces of pumice are largely dispersed between these two yellow lines and originate from a vent that lies underneath this lava dome right here. And as we move further away from the vent, pieces of pumice get progressively bigger. So let me return to those open questions. From the mapping and satellite images, we can obtain the erupted volume and the eruption rate. We now have a sense of what the deposits from these eruptions look like, both the pumice and finer materials, as well as the lava flows. And we know something about the history. First, the raft formed in the giant pieces of pumice, and then the lava dome erupted afterwards. So now we'd like to understand how it is that the magma erupted and how this pumice got up to the ocean surface. And to do so, we're going to rely on measurements we can make on the samples we collected, the mapping, as well as using models and lab experiments. So let me return to the picture I showed you earlier, where we saw that as magma is rising and bubbles are growing, the magma is going to accelerate. And the primary way in which magma fragments in subaerial volcanoes or on land is if the melt is deformed too quickly. For a liquid to be able to flow, its molecular structure has to be able to rearrange itself fast enough to accommodate the applied deformation. And if it can't, it can become brittle and it can break. And I'll try and do a little demonstration for you with some of a process you're hopefully familiar with. If I take a piece of silly putty and I pull on it slowly, deformation rate is low and it stretches. And if I pull on the same piece of silly putty fast, it becomes brittle and it can break. And this is the primary way in which fragmentation occurs in subaerial volcanoes. And just looking at this picture, you can see the kinds of measurements we will need to make. We need to know how much volatile elements, species were dissolved in the magma depth, the pressure at which the magma was stored, how the gases escape as the magma rises up to the surface, and what gives rise to the fragmentation. So here's a list of some of the properties of this magma and the boundary conditions that we know. I don't have time to explain how we know it, but we know the eruption rate, we know the melt temperature, we know its composition, which allows us to compute the viscosity. We know how much water was dissolved in the magma at depth. We know the depth at which it was stored and the pressure of the vent. So what we'll do next then is solve the equations for conservation of mass, momentum, and energy that describe the processes that you see in this cartoon to look at how properties of the magma change as the magma rises to the surface. So what I'm plotting here on the vertical axis is depth below the seafloor, and we're looking at a variety of properties of this magma as it rises. On the far left is a plot of pressure, and you can see that as magma rises, the pressure decreases. As pressure decreases, solubility of water decreases. So the water comes out of solution to make bubbles, and the volume fraction of bubbles increases, reaching 80% at the vent, which is what we see in the erupted pumice. As water goes from being dissolved in the melt into the bubbles, the amount of water dissolved in the melt decreases and viscosity increases. Now the key panels, the second one from the left, it's the strain rate, the deformation rate of the magma, divided by the deformation rate needed to fragment. And this number is always much less than 1, so we cannot undergo brittle fragmentation. Now at 80% porosity, the magma that enters the ocean is less dense than the ocean, and so would continue to extrude and float up towards the surface. You can imagine that this magma being 850 degrees Celsius is going to cool and quench into the ocean, allowing it to break. If the fragments that form from this quenching are big enough, they can float away from the extruding magma fast enough to float up towards the surface. Now this bubbly magma that's breaking apart in the ocean is hot, and the ocean water, of course, is cold, and it's going to cool the piece of pumice, and this is going to cause the gases inside of it to contract and condense, drawing still more water. And if enough water gets ingested, the piece of pumice will become more dense than the ocean, and it can sink to make the giant pumice we see on the seafloor. And I should have pointed out that if fragments are bigger than about 1 meter, they're able to float up to the ocean surface and separate from the extruding magma. So now to determine whether the pumice can reach the ocean surface before ingesting enough water to make them sink, we develop again models that solve for the conservation of mass, momentum, and energy as water flows into the piece of pumice. And we do lab experiments in smaller pieces of pumice than the giant pumice anyways, to test these models. And so what I'm plotting here on the vertical axis is the time it takes for the pumice to float up to the ocean surface as a function of their size for different porosities. And these curves only begin if the piece of pumice can reach the surface. And so provided the piece of pumice is bigger than about 1 meter or so, it's able to reach the ocean surface where it can float. This raises a couple other questions though. Why does pumice continue to float on the surface of the ocean? In fact, after floating for months to years, pumice can eventually sink. So here we do experiments where we take pieces of pumice, we heat them up to a variety of temperatures, we put them on water, and we look at how water enters the pumice. And like Isabel showed you in the first talk, we can use X-ray computed microtomography to image the fluids inside this rock. So I'll focus on the 2 images on the right. The white shows the glass, the solid. Blue is liquid water, black is trapped gas. And for the pumice we recovered from the seafloor, liquid water is efficiently and effectively able to fill up and enter all the pore space. Whereas for the pumice we collect from the raft, as the water enters, it traps gas. And in fact, these pieces of pumice often have isolated bubbles completely detached, surrounded by melt. And there's enough gas that can be trapped to allow this pumice to float. Now, over time, these bubbles that are surrounded by liquid allow gas inside these bubbles to diffuse through the water to the outside of the piece of pumice. And this will allow the pumice over time to get more dense. But since this is a diffusive process, this time scale will scale like the diameter of the piece of pumice squared. And sure enough, in our lab experiments, we find that the duration of flotation scales with the diameter of the pumice squared for the pumice that eventually sinks. So let me return to this illustration again. We said there are 2 fundamental ways in which volcanoes erupt: explosively, if the magma can fragment, effusively, otherwise. And one way to get an effusive eruption is to have the gases escape from the rising magma. Now, as the eruption progresses, you can imagine that the pressure driving the magma to the surface is going to decrease. As the driving pressure decreases, the magma is going to rise more slowly, allowing more time for outgassing of gases inside those bubbles. And so then a more dense magma can be extruded to the surface to make our effusive eruptions. I actually very intentionally picked the St. Helens comparison here because the eruption rate for the explosive eruption is similar to the raft-forming eruption at Havre, and the eruption rate for the effusive eruption is similar to that made the lava domes we see on the seafloor. And in fact, if we look at the textures of the magmas that erupt, we can see evidence for gas loss during ascent. On the left, these are scanning electron microscope images with a scale bar in the lower right. We can see nice rounded bubbles from the raft pumice. Whereas the samples collected from the dome, we have irregular bubbles as the bubbles are collapsing as gas is flowing through the magma. And highlighted in purple here is the mineral cristobalite, SiO2, that precipitates out of vapors flowing through the lava dome. So some of the questions we were hoping to answer: does magma fragment in the conduit? We think the answer is no, but instead the magma is fragmenting as it enters the cold ocean. If pieces of pumice are bigger than about a meter, they're able to float up to the ocean surface. If they can trap enough gas, they will float, and they can float for a long time. And pieces of pumice that don't trap gas sink to the seafloor. And the transition to the effusive eruption is controlled by gas loss during ascent. So I illustrate these processes in this pair of cartoons. There are a number of numbers on these cartoons, and these are all numbers we obtained from the models as well as measurements made from the seafloor. So again, the raft forming stage, buoyant bubbly magma is extruded into the ocean where it can quench, and big pieces of pumice can float up to the ocean surface. As the eruption rate decreases, progressively more vapor is lost to the surroundings, allowing a more dense magma to erupt to the seafloor where it makes the lava dome. And of course, it's these vapors and fluids that are leaving the ascending magma that transport with them metals and ultimately form ore deposits, copper and gold deposits. These types of submarine raft-forming eruptions are not exactly uncommon. Here's an image taken by a sailing vessel on August 9 of last year. You can see subtle waves underneath this raft. In fact, that image was taken 2 days after the eruption began. We're now looking at an unnamed island, some unnamed volcano in the Tonga Islands, only 200 meters below sea surface. This was a much smaller eruption, about 100 times smaller than the Havre eruption. But conveniently, the sailing vessel passed through the raft early on, so we can get pristine, fresh samples. Just a couple images to give you a sense of what these rafts look like. In the upper left in A, the actual initial blast or eruption was captured in a satellite image. You can see the picture in the upper right of the raft. The raft is the brown color. Light blue shows little bits of glass that are produced by abrasion sinking through the water column. These rafts have quite complex shapes with long stringers. And in panel F, you can see that the raft eventually washes up onto beaches. We can use a variety of satellites to keep track of the position of the raft over time. On the top, we're looking at its position over 1-day intervals, and on the bottom over a 1-month time period. And the significance of being able to track the raft is we can compare the position of the raft in these images with predictions from a model that accounts for ocean currents, wind speed, as well as the effect of waves. And we can then use those models to forecast where the raft is going to go. And this, in fact, was done, and information was communicated bi-weekly to authorities. On the right is a forecast over the next 2 years of how many pieces of pumice in the top will pass by a given location on the surface of the Earth. And on the bottom, the average time it takes for pumice to reach a certain location. And so the forecast here is that in about a year, this pumice will be rafting up onto the shore, onto the beaches in Australia. Briefly, what's next? We did have 2 more cruises funded for October and then again in November. When and how these happen, I'm not sure. The first is to study the evolution of the hydrothermal systems enabled by these eruptions, as well as to document the biological recovery of disturbed seafloor communities. And the second cruise is aimed at looking at deposits from much larger submarine eruptions from this volcano. These were caldera-forming eruptions that created the caldera or large crater you see in the middle here. These would have been underwater equivalents of the on-land pyroclastic flows, but much larger. And these are responsible for these large fields or waves of sediment you can see on the flanks of the volcano. So to summarize and wrap up, buoyant magma was extruded into the ocean. It created large pieces of pumice. Some sank, but most floated. The eruption rate was similar to Mount St. Helens in 1980, though the erupted volume was greater. And something I did not highlight, but was embedded behind some of the results I showed you, is that we did benefit tremendously from being able to integrate a broad range of expertise in multiple disciplines and the efforts of a very large number of people. And there's no on-land equivalent of these submarine eruptions. The ocean pressure suppresses fragmentation by increasing the solubility of water in the melt, which keeps the viscosity of the melt lower. But quenching in the ocean allows fragments to form. These fragments can float, and the products of this eruption are no longer preserved near the volcano. So returning to the erupt report that I mentioned earlier, one of the grand challenges was to quantify the life cycles of volcanoes globally to overcome our biased understanding. This is especially true in the submarine realm, where we know very little about the life cycle of volcanoes, the processes that govern their eruptions, and the fate of the erupted materials, and their impact on other Earth systems. But given the chance to explore, we are learning something, and I think we're learning that underwater volcanoes can be quite different from those that we know about. And I think I'm going to stop here, and I'll let this video run in the background while I start answering questions.
Okay, sorry, it took me a minute there to get unmuted.
No worries, it was 1 minute long.
No, perfect, thank you. I am looking, the chat room looks, I'm waiting for some hands here. Could you tell, oh, here's one, but just out of curiosity, could you tell us what we were looking at in the beginning of that, the topography we were looking at in the beginning of that video? And then I'll say that Nelia has a question after that.
Okay. Yeah, that was actually not the Havre volcano. It was North Mata, and it's a little underwater equivalent of a Strombolian eruption. I think the vent in that case was just over 1 meter. Great. This piece of pumice that's being recovered here was 1.5 meters in diameter.
Wow. Great. Nelia has a question.
Okay,
I'll answer Dennis.
Michael, thanks for a terrific talk with just lovely imagery. I really enjoyed that. I have a question about some of the big pumice that didn't float. And you may have addressed it, but I didn't quite get it. So I might speculate that some of that big pumice that didn't float might have been in a eruptive phase that was transitional between the early phase of the eruption when volatiles were not able to escape through the conduit walls, and you had that fire hose of rhyolite pouring into the ocean. Transitional between then and the lava domes. But I think one of the images that you showed, one of the tomography images, showed that some of that sunk pumice is actually very expanded. And I'm wondering if you could elaborate a little bit more on that, because I might have missed it during the talk.
Yeah, excellent question. And so it is an open question. What is the relationship between the pumice we see in the raft and the pumice we see on the seafloor? They have essentially the same porosity. And so that would suggest that they erupted at roughly comparable rates and they lost comparable amounts of gas during ascent. There is a difference in texture between much of the seafloor pumice and the pumice in the raft. Much of the pumice we recovered from the seafloor has elongate, stretched bubbles, tube pumice. And so I think what separates the pumice in the raft from pumice on the seafloor is simply if you're able to ingest enough water, you sink. If you don't, you float. And the vast majority of pumice came up in the middle of the conduit, didn't allow the bubbles to get very well connected and stretched, and making it harder for liquid water to infiltrate into the pumice. So it's really the ability to ingest water becomes a filter to separate pumice that floats versus pumice that sinks. There's some questions. Should I answer the questions in the chat box?
Yeah, I was going to field those for you, but yes, please. And would you ask the people to introduce themselves very briefly as to their affiliations?
Okay, so I don't know Luciana Estes personally, But she asked a good question about, are there seismic signals? And of course, in hindsight, we can look back through the record of seismicity and identify the earthquakes that occurred on the day of the eruption. The biggest was a magnitude 5.4. The absence of a good network of seismometers covering this part of the ocean makes it difficult to get very precise locations. And so all the seismicity locates to within about 20 or 30 kilometers of the event. She's from the National Science Foundation. Excellent.
Great.
There are, of course, earthquakes happening all the time in these volcanic arcs. And most of them are not associated with eruptions that we see at the surface. We have obtained access, though, to the CT-BTO hydrophone data, but have yet to see if we can locate the distinctive signals of the eruption. But it would be nice to know what the history of the eruption is more precisely. Dennis Geist, also at the National Science Foundation, asked about the extent of international participation. I would have to go back and look at the image, but Rebecca Carey, who was one of the two co-chiefs, was based at the University of Tasmania, along with Jocelyn McPhee. There were also scientists from New Zealand and Ken Tani from Japan.
Great. I don't see any other hands. All right. Well, I think that we have a break coming up. 15 minutes. I think we have 3 extra minutes. Thank you, Michael, for making that happen. We will return, or people can stay online, of course, but we'll return officially at 1:30 your time, and corrected time for anybody else in other locations. And we'll start with a talk by Bill Hammond on Geodesy. All right, see you soon.
Great. Thanks, Isabel. Thank you, Michael. We'll see you at 1:30, everyone.
Yeah. Yeah, thank you very much, Michael. It was great. Michael, since you're still on, we have 2 more questions. We'll start with, actually 1 question, but we'll start with.
I can answer Scott's question.
He's still on too, but I think that so that everybody can hear it. I don't know who's on or not. So we'll start with that at 1:30. Well, okay. Yeah, is that right?
Yeah.
Hello, everyone. We should be starting in about 1 minute, so please get yourselves settled, and we look forward to the second half of our Board on Earth Sciences and Resources meeting. Good afternoon, everyone. This is Elizabeth Ada. I want to welcome you back to our session, the virtual spring meeting of the Board on Earth Sciences and Resources. and I'm going to turn the floor over to Isabel Montañez, who's going to continue moderating our session this afternoon. Just wanted to remind you all that we are recording this session and plan to post the session online approximately 7 to 10 days after this meeting takes place, so that you can have that on your website. And we'll be back in contact with you once the meeting is posted. So Isabel, I'll turn the floor back over to you, please.
Great, thank you. So it's a great pleasure to introduce our next speaker, the third of the four. And this will be our talk on geodesy by Bill Hammond. He is a professor of geodesy and geophysics at the Nevada Geodetic Laboratory, which is affiliated with the Nevada Bureau of Mines and Geology at University of Nevada, Reno. And Bill has done extensive research using space geodesy to study a wide range of active processes on Earth, including active seismicity. And I think that he'll be speaking about some of that today. He has been involved as the chair of the advisory committee for NSF-supported EarthScope that I think everybody is familiar with, and quite active in other professional activities as well. So, Bill, I'm going to turn it over to you.
Okay. Hello, everyone. Thanks for coming. I just need to figure out how to advance the slides myself.
It's probably going to be a bit of delay, but it should be with using your arrow button. Your arrow, I think your arrow button.
Oh, it looks like something's happening. Okay.
Yep.
Oop.
Yeah, a bit of delay there.
Okay, we'll work with it. Okay, it's flashing around, but I think that's the first slide. Hello, everyone. I'm Bill. Today's somewhat diverse audience, so I thought I would start by first saying what geodesy is. Geodesy is the science of studying Earth's shape, how it changes over time, also its gravity field, and its orientation in space. So the Earth is constantly moving and deforming owing to various forces that are placed upon it. This includes motion of the tectonic plates, the tides that squeeze the Earth, and the oceans and atmospheres that flow around and load its surface. So there are many processes that deform the Earth. And I'm going to talk about a couple of cases where measurement of the active Earth deformation using GPS networks has revealed or confirmed aspects of how the Earth is working. So I'm going to focus in particular on vertical motions, since they can be directly or indirectly related to the building of big mountains, such as the Sierra Nevada, which are shown here. I usually work in Nevada, Eastern California, and other parts of the Great Basin, but in spring 2019, I was very fortunate to take a sabbatical in Rome, Italy, to study the Apennines. So there's an alternative title to the talk, and I want to go to the next slide. Let's see if it works. Did it change? I'm trying to advance to the next slide, and that's it. A tale of two ranges, active uplift of the Sierra Nevada and the Apennines. So I work in Reno, and you can perhaps be forgiven if you think of Reno, Nevada and Rome, Italy as very different places. But aside from their similar names, they do share some other things in common. So next slide. Working? There we go. So a cursory comparison between these two places, these maps are both on similar scales, shows that both California, Nevada border region and the Italian peninsula are dominated in their topography with these very long mountain ranges. They're both about 800 kilometers long. And the Sierra Nevada has the basin and range to the east. Both of these places experience crustal deformation that drives extension and normal faulting, and earthquakes. The Sierra Nevada has the Basin and Range, and the Apennines are extending owing to the Adriatic plate pulling away from the Tyrrhenian lithosphere and driving extension along the crest of the Apennines. So earthquakes in both places are a major concern, and active monitoring of crustal deformation attributable plate tectonics is ongoing. So before I get into too many of the details on this, I want to touch a little bit on a connection with some recent National Academy activities. There's just this year, a writing group coordinated by the Committee on Seismology and Geodynamics of the National Academy completed a report on evolving the geodetic infrastructure to meet new scientific needs. And the global GPS network is an example of this geodetic infrastructure. So currently we can show as a indicator of the status of these geodetic networks, a map of all the stations that are processed by our group, the Nevada Geodetic Lab. The map shows about 18,000 separate locations where there are continuous GPS stations on Earth. And each of these points provides open data with latency of between seconds to weeks, giving us a daily 3-component precise position of better than a millimeter in the horizontal, and usually less than 4 millimeters in the vertical. And this is accomplished through the International Terrestrial Reference Frame. So with this network, we can see that the location of, we know where the center of the Earth, center of mass that is, to better than a centimeter per year. The coverage is pretty uneven and tends to dominate places where there tend to be earthquakes or there tends to be resources, i.e. money that is available to establish these networks. So the report detailed some of the applications for these networks, including sea level change, geologic hazards, terrestrial water cycle, weather and climate. And I'm going to talk about just a couple of scientific applications from these networks. Yes. Okay. So when we talk about big mountain ranges like the Sierra Nevada, we see them as obvious artifacts of vertical land motion that occurs over millions of years. Geologic studies of normal faults on the east side of the Sierra show that they accommodate vertical motion at rates between 0.1 and 2 millimeters per year. In this case, I'm showing the Genoa Fault, which is south of Reno, Carson City. And this fault is active. It's had a couple of big earthquakes over the last 2,200 years. And its vertical slip rate is on the order of 1 to 2 millimeters per year. So it's similar to the Wasatch Fault in Utah in terms of its capacity to have large earthquakes. And this fault builds the Carson Range and holds in Lake Tahoe there in the background. So a big question we have is whether we can see uplift using very precise measurements from of how elevation and GPS stations change over time. Okay, so we have quite a lot of data now from the various networks. The red dots in this map are our own that we operate out of UNR, the Magnet GPS network. It's a semi-continuous network. Magnet stands for Mobile Array of GPS for Nevada Transtension. And we circulate about 80 receivers through 400 various measurement locations. The blue stations are those from other precise networks, including the NSF's Network of the Americas, which is a continuous network that was developed through EarthScope. But all the networks, there are other networks as well, but all of them have the same kind of, provide the same kind of dual frequency data that we need to get the very best precision. So what follows, I'm gonna skip over a lot about data processing and algorithmic work that's near the core of what we do, in order to get to some other topics. But to suffice us to say that from each of these stations, we solve for the vertical rate of motion in a robust way, and we get a map of the vertical rate field for the California, Nevada area, and there it is. And this vertical rate field, I should explain, the color scale is downward is blue, and red is upward, and the scale saturates at -3 millimeters per year downward and 3 millimeters per year upward. And this is placed into the, it's aligned to the International Terrestrial Reference Frame, the latest version, IGS 14, which means that the motion is with respect to the Earth's center. So some of the features we see include these blue subsidence areas in the California Central Valley, which are actually much faster than the limit of the color scale. It's very much saturated. In the actual downward rates, there are 1 or even 2 orders of magnitude faster than the 3 millimeter per year limit. We also see a halo of uplift around the subsidence in the San Joaquin Valley, the southern Central Valley, which has been thought to be a crustal unloading effect from the water that's been taken out of the aquifers in the valley. So that's a rebound. So a lot of that signal is associated with water and losing water on their surface. There are other signals in this field that are associated with the Earth's cycle. Down in the Mojave, there's post-seismic relaxation from the Landers and Hector mine earthquakes. Northwest, there's red up in Northwest California associated with Cascadia interseismic strain accumulation on the subduction zone. And out in Nevada, there's a big red blob out in the middle of Nevada there. And we call that an earthquake ghost, since we think it's a lingering mantle relaxation from earthquakes that happened from 1915 to 1954. So that post-seismic relaxation is persisting for many decades. Okay, I'm not sure I can point to it the way things are going here, but in Eastern California, near the edge of the Eastern Sierra Nevada, there's a reddish spot there. Oop, I'm supposed to move my pointer and annotate all these different uplift signals. And right here, there's a very rapid uplift that's associated with the Long Valley magmatic inflation, which is a large caldera system in Eastern California near the town of, the ski town of Manga. Okay. And my pointer is doing strange things. Okay, so let's go to the next slide. So, whoop, sorry folks. I can only see a part of the screen for some reason. So what I showed you in the last slide was how the uplift varies over space. And this slide is showing you how it's varying over time. So the blue dots in the time series are all are from 22 separate GPS stations on the west slope of the Sierra Nevada, and they've all been just stacked together. So you can see that the signals in all of them are relatively similar. And they show over time an uplift, a steady uplift of about 1.5 millimeters per year. However, there's also some other signals in there that are important. The wiggles, the annual wiggles are attributable to seasonal loading of water on the Sierras that moves the range up and down. And you can also see that there are periods where the rate of uplift is faster and sometimes than others. For example, between sort of 2011 to 2016, the rate of uplift was faster than the average. And we puzzled over this for a while until we started paying more attention to the weather and climate indices. In particular, the PDSI here, shown in a red time series, is the Palmer Drought Severity Index. And that's based on precipitation and temperature data, and indicates wet versus dry conditions compared to normal. So the sort of the shaded areas are parts where there are these multi-annual lows in the PDSI, which indicate relatively dry times, i.e. droughts. Okay, we also look at GRACE data. GRACE is a satellite system. It stands for the Gravity, Recovery, and Climate Experiment. And it's basically a satellite system that measures the Earth's gravity field over time. And it does this every month. It gets a gravity field for the entire Earth. And these gravity changes are largely from variations in water mass on the Earth's surface. So GRACE shows a strong seasonality as snow and lakes and aquifers fill in the winter and dry in the summer. But it also sees periods of drought. So there are inflections in the trend in GRACE that match the times where the PDSI is in a dry period, and also periods where the GPS rates are going up on the Sierra Nevada relatively fast. So it looks like the range is responding to the dryness through an unloading effect and going up in dry periods and down in wet periods. Okay. Okay, so remember I mentioned that the Long Valley Caldera system in Eastern California was rising very quickly. It sits on the eastern edge of the Sierra Nevada in the Central Walker Lane. And this area has been active. It's an active magmatic system with a magma chamber 6 to 10 kilometers deep, which has been causing tumescence, seismicity, and sporadic gas discharge since the 70s. This inflation in the middle crust drives up the Earth's surface about 10 times as fast as the uplift of the adjacent Sierra Nevada. And we can show with the GPS data that the Long Valley magmatic system is feeling the hydrological loading of the Sierra, which sits right next to it. Okay, and this is to show for the distribution of GPS stations we have around the area. Long Valley has been intensively monitored with geophysical instrumentation, including seismic, leveling, gravity, gas, and GPS semi-continuous and continuous networks for quite some time. There's one station, RDOM, it's in the magenta here. I don't know if you can see my pointer, but it sits right in the middle of the caldera, right on top of the resurgent dome, which is on top of the magmatic system, near the middle of the inflation. So if we look at the data from RDOM, that's the blue dots along here, it's very sensitive to what the magma chamber is doing. And it's basically indicating that its movement is highly exaggerated compared to the movement of the Sierra Nevada. So the blue is what the magma system is doing. Whoops, I didn't mean to do that. The time series at the bottom is the median motion for the Sierra Nevada, and the time series above are those for the Long Valley magmatic system. And you can see that the periods of inflation are in sync with the dry periods that occurred over the last 20 years or so. So it appears that, in particular, the drought time that started in late 2011 seems to be associated with the initiation of a very rapid inflation period of the Long Valley caldera. Okay, so that's what we call, we suspect, a triggering possibly associated with an unloading of the magma system helped encourage inflation during that time. Okay, so I'm going to move to to another continent for a little bit and take a breath and think about another mountain range while we enjoy the flow of the Tiber through the middle of Rome. So this is part of the talk as a result of a collaboration that I had with Nicola D'Agostino at the INGV in Rome. And he's been studying GPS networks of the Apennines for a long time. And our project was to use a new compilation of GPS solutions that Nicola has developed and use them to study the uplift of the Apennines. So I'm going to talk a little bit about, having a hard time with my slides, folks. There it is. Ooh. Okay, so the map below, the Apennines lie in the same area where most of the tectonic plate boundary extension occurs as the Adriatic microplate pulls away from the Tyrrhenian lithosphere on the left. So I'm going to show you the location of several profiles of topography, east-west, from the Tyrrhenian to the Adriatic coast. This shows the topography and the location of the drainage divide, which is important for the long-term erosional effects on topography and the topography's effect on drainage, depending on how you look at that. Okay, so next. All right, so this shows the location of the Apennine topography with relation to where the GPS velocities, these are horizontal GPS velocities, in the center figure show the Adriatic microplate pulling away from the Tyrrhenian and focusing the active strain rate in places where there are a lot of the earthquakes and also the Apennine drainage divide. So let's look at the vertical results. It's the same color scale as before. The red is up and the blue is down with the same 3 millimeters per year color limits. And okay, so the little circles are the locations of the GPS stations. We've corrected for the vertical motion attributable to glacial isostatic adjustment, which is a signal that covers most of this area. And it's associated with the loss of continental ice sheets in Northern Europe. So we've made the average motion in this area 0. And what we see is mostly continuous uplift along the entire length of the Apennines, all the way to Calabria and crossing into Sicily. It's tending towards subsidence on the Tyrrhenian and Adriatic coasts. And some of the uplift to Sicily is not just from the volcanic transients in Etna, but is actually part of this stripe of uplift that goes all the way down the peninsula of Italy and into Sicily. So there's very little data in the Dinaric Alps on the other side of the Adriatic, so the resolution is not very good there. Okay, if we look at those profiles, we can see that the signals are fairly small. They're on the order of 1 to 2 millimeters per year, similar in scale to the Sierra Nevada. They're median filtered and smooth in this gray envelope that captures the data, but we can see that there's a couple of humps in the vertical rate field. One of them is definitely focused on the drainage divide, and the other hump is near another topographic high, but the uplift rates follow the topography somewhat, and it's a quite wide hump in the vertical rates. And none of the signals seem to be particularly focused on any individual fault system. So it's a very wide and broad arching of uplift. Okay, so if we look at the horizontal signals using the same technique. We can look at the horizontal velocities in a Eurasian reference frame and grid them and calculate strain rates from those horizontal velocities. And those show us the rate of deformation, active deformation of the crust, is also somewhat focused on the Apennine crest and the drainage divide. So it appears to be located in a very similar place with this strong stripe of extension is in the pink color and contraction is in the blue color. So we can see that extension very well. The horizontal deformation data has much lower uncertainties compared to the signal. So we're very confident of where that is. It also shows that there's a secondary, weaker, though active bend or band of deformation west of the Apennines, which is near the zone of the secondary zone of active uplift that we saw in the previous profiles.
Bill, can I give you a 2-minute notice?
Yep. Yeah, I'm getting there. Okay, so our experience with the Sierra Nevada was helpful here because we went into it being somewhat suspicious that the uplift that we saw could be from a hydrological source. So we needed to answer the question for the Apennines: is the uplift a temporary blip owing to a drying period, or is it a long-term effect associated with large-scale geodynamic processes? So we address this in several ways. One of which is to look at the GRACE data again, which measures changes in water over the Earth's surface. And when we look at GRACE, we find that the trend is actually for increasing amounts of water on the surface in Italy rather than decreasing amounts that we would need to explain uplift with some sort of unloading from water from a drying period. So the trends tend to be wetting, the opposite that you would need to explain the uplift with a hydrological source. So that suggests that the uplift is not hydrological and possibly associated with a plate boundary scale process. Okay, so this last slide, this is my second to last slide, is more of it's a little bit text heavy, but it summarizes the arguments for why we think that the uplift that we're seeing in the Apennines is a mantle related uplift. And this has been discussed extensively by others, including Thorsten Becker, in publications that go back many years. But we focus here not just on topography, but topography that's actively increasing over time. So it suggests that the mechanism that's increasing the topography may be similar to the mechanism that is supporting the topography. So we already addressed the hydrological unloading. We think, no, it's not that. Is it an earthquake cycle effect, like a post-seismic in central Nevada? We don't think so because we don't think all the faults in the Apennines can be timed together. Is it erosion? It may be partially erosion. Denudation of the Apennines could unload the lithosphere, but rules of thumb suggest that the erosion rates that are present are not high enough to unload the crust enough, making this, sorry, making that an unlikely explanation for all the uplift. It could be partially a flexural response associated with extension, like in the East African Rift, Baja California, or some mid-ocean ridges. But the plate is fairly thin in the Apennines, so it probably would not give the very broad uplift that we observed. So if its support is simple isostatic compensation or even stationary dynamic support, then the active extension would drive subsidence, opposite to what we observe. So together, these suggest that the support comes from underneath and is increasing to drive the increasing elevation in what we call an upwelling. So that is the end of the talk. I have just a few excuse me. Points, which I actually can't read because I don't have them all on my, I can only see a part of my screen at any one time for some reason on the talk. So I'll leave them there and I will open it up for questions if anybody has them.
Thank you, Bill. I will wait for some people to write questions or hands to go up. Oh, I see Nelia has one, and then I have one as well. So let me, Nelia, would you like to ask your question?
Okay, I think I'm unmuted. Thanks, Bill. That was a lot of really interesting information in that talk. And I had a question about Long Valley. So you mentioned that the uplift in Long Valley associated with the magma chamber there is very high, and then quantified that. And you saw this interesting feedback between droughts and uplift in the area where the magma chamber is located. And one possible thought process there might be, as you unload the magma chamber, you get more, you have more volatiles that move into solution and might escape the magma chamber. And I know there's a lot of active gas monitoring going on around Long Valley. Has there been any gas signal detected associated with this?
Not in one that's timed. There's not the gas monitoring that exists. I don't think is continuous. That they do gas surveys sometimes, and there's obvious signs of gas like tree kills and obvious, and there have been situations where there have been gas burps that have been even fatal to personnel at Mammoth Mountain who have gotten stuck in holes. But I haven't found any time series of gas that can be correlated with these periods of unloading that inflate, that are associated with an inflation in the magmatic system. So I think that the timing of this is important too, because the stress, when on the load, the stress propagates down to the magmatic system very quickly. So the magmatic system will feel the load almost instantaneously, whereas any gas escape related to that would probably take some time to get up and out. So whatever study of that would have to take that into account. There has been other work that shows that rainfall is in the Sierra is associated with increased seismicity, particularly around the south moat, but those effects are not quite as deep as the 6 to 10 kilometer depth center beneath the resurgent dome, which seems to be driving the inflation.
Great. I had a quick question, but I'll ask you separately. I wanted to hear what you had to think about the long-term droughts of the past, whether dating is sufficient to be able to see what those relationships might have been. But let's skip that. We can chat offline on that one. Well, the last question will be from Scott, and he asks, looks like the GPS expression inflation at Long Valley is significantly accelerated since 2012. What does this mean for eruption hazard there?
Well, it's been thought that the overall magmatic system of Long Valley is kind of in a waning mode compared to, say, 600,000 years ago, when it had an eruption that developed the caldera and threw ash halfway across the United States. But it is still very active. There's seismicity, there's the things I mentioned before, the active inflation. And so it's not dead. It's definitely a thing that is alive and poses a risk, and it's monitored by the USGS. And so whether these increased inflationary episodes are harbingers of some sort of future eruption, that's very much unknown. They've happened a lot of times without forming any kind of eruption. So it's not necessarily a predictive tool, but it's certainly something that we would like to pay attention to. There are indications in the geologic record that periods without glaciation were periods where there were a greater amount of volcanic eruptions. This has been observed in Long Valley. I think Michael was involved with a study in Long Valley on that, and also in Iceland. It's been observed that glaciers that load the axis of the rift there seem to suppress seismicity and inflation. So it's something that has been observed in other places, but this is maybe a much finer, lower amplitude and more sensitively measured version of that.
Great, thank you very much, Bill. And I just add to that that it's been posited as well for the mid-oceanic ridges, for the glacial interglacials. But thank you for a great talk. Okay, our fourth of this four-part series talk will be by Estella Atekwana, and she is currently the Dean of the College of Earth, Ocean, and Environment at the University of Delaware. Prior to that, she was the chair of the Boone Pickens School of Geology. And Stella's research interests there are quite variable and interesting. There are areas of biogeophysics and tectonics, and she'll be speaking about the former and specifically about the geophysical signatures of microbial cells in the subsurface and their implications. Estella.
Listening. In fact, this is a part of a global virtual lecture. Hopefully everybody can see my screen. Is that correct?
Yes, we can.
Okay, great. And so it's part of a global lecture, virtual lecture. I'm a Society of Exploration Geophysicist 2020 Near Surface Geophysics Global Lecture. And so I was asked to give this very slimmed down version of the lecture. So what I hope to be able to do this afternoon is to provide you with a broad overview of biogeophysics and the work that is coming out of the near surface geophysics community. So I'm going to start first by trying to define biogeophysics, because I assume that many people may not have heard about biogeophysics or even know what it is. And then I will share some case studies that look at the geophysical signatures of microbial activity and some, thoughts about what we can do in the future to use geophysics to advance astrobiology type studies. I would like to start with this particular slide, and it's a figure that came out of our 1998 paper that really made the first connection between changes in geophysical signatures induced by microbial activity. And the data was acquired at a hydrocarbon contaminated environment. So the top figure is the ground penetrating radar profile, and the middle figure is the electrical resistivity profile. And what we see here is that there's a region of attenuated ground penetrating radar signals that is coincident with a region of elevated bulk conductivity. And for your color scale here, reds are low resistivity or low conductivity, and the blues are higher bulk electrical conductivity or low resistivity. And the interesting thing about this study is that until when this study was conducted, we always assumed that hydrocarbon contaminated environments should be resistive, because we know that petroleum products or oil is resistive. But what we found working at this particular site is that instead of recording the resistive signature, we had the opposite. And so in trying to explain the difference, in reading through the literature, we recognized that microorganisms, or we discovered microorganisms based on some geomicrobiology studies and biogeochemistry studies, actually break down the hydrocarbons, and the byproducts of these metabolic reactions included carbon dioxide and some organic acids. And so this acid enhanced the weathering of minerals as shown in this particular SEM image here. And when that happens, you release ions that go into solution. So for example, I'm just showing an example here of calcium ions. And we can see that there's a region of elevated calcium ions, which is coincident with the region of bulk, enhanced bulk electrical conductivity. And so what we were able to do then is to suggest that the elevated pore water conductivity resulting from the microbial breakdown of the hydrocarbons resulted in this enhanced bulk conductivity, which also could explain, the GPR response. So this body of work, so today a large volume of literature from the near surface geophysics community has really established that microorganisms can in fact impact geophysical signatures. And the body of work now has helped to shape the new field of biogeophysics. And so we published a review paper in 2009. If you want to find out more about biogeophysics, you can get this. It's published in the Reviews of Geophysics. And essentially we defined biogeophysics as an interdisciplinary science that spans the established disciplines of geomicrobiology, environmental microbiology, biogeochemistry, and geophysics. And it is concerned with the study of geophysical signatures resulting from the interactions of microorganisms and earth materials. In short, geophysical techniques do not only measure subsurface physical and chemical properties of the subsurface, as geophysical methods are conventionally used, but they can also be used to image subsurface microbial activity. So unbeknownst to us at that time, is the fact that microorganisms, in fact, are architects of rock transformations. And geomicrobiologists have already established this. Microbes are everywhere. They're found in almost every habitat on Earth. They are involved in practically every aspect of the evolution of the Earth, including climate change, serving both as producers and consumers of greenhouse gases, and they participate in many biogeochemical reactions. They are not passive, as we may think, just because we don't see them, but that they are catalysts for geologic change. And they play a very important role in accelerating many Earth processes, transforming our physical Earth and mediating different biogeochemical cycles. So they participate, for example, in the formation of new minerals, as well as they can destroy minerals. They've been implicated in the formation of banded ion formation, and although occurring at a micron scale, they can transform rocks at a large outcrop scale. So what I like to do here in this particular slide is it's kind of like a summary slide that shows the different pathways by which microorganisms can change rock physical properties and the corresponding geophysical techniques that can be used to image that particular process. And so, for example, and I've labeled them 1 through 5. We start with 1, we look at just the microbial cells themselves. Microbial cells, they have an electrical double layer surrounding them. So they have electrical properties. And if that's the case, then it says that electrical geophysical techniques can be used to detect the presence of microbial cells in the subsurface. And the second example here, or pathway, the microorganisms, they grow attached to mineral surfaces, and to do that, they excrete. They produce exopolymeric substances or some slime or sticky substance that allows them to anchor themselves onto the rocks. And when they do that, these biofilms, as you can see in this picture, have properties. In fact, they clog the pores, and therefore they change the mechanical properties as well as elastic properties of the subsurface. And therefore, seismic techniques can be used to image the presence of biofilms in the subsurface. In the third example, like I already showed you from the example from the hydrocarbon contaminated site, is that the microorganisms, as part of their metabolic byproducts, can change the pore fluid chemistry. This is an example from the Taylor glaciers in Antarctica, an area that's known as blood falls, and this is iron-rich waters that are coming out from the base of the glaciers. And again, so changes in pore fluid chemistry can be detected by electrical geophysical techniques. We know that microorganisms can also produce gases as part of their byproducts, and some of these gases could include carbon dioxide or methane, and we do know that gas can in fact impact both seismic and electrical properties of the subsurface geologic formations. And then lastly, through microbial-mediated redox reactions and the biogeochemical cycling of some elements, for example, iron, microorganisms can precipitate minerals that will occupy the pore spaces. These minerals can either be conductive or they can in fact be magnetic, like in the example here I'm showing you, magnetite that's been produced from microbial activity. So what I like to do now is to show you examples of some studies that have been conducted that highlight each of these different pathways and what the geophysical signatures look like. So let's look at some case studies then. So first, our first pathway was to look at microbial cells. And you may be wondering, why would anybody want to be able to determine the presence of microbial cells in the subsurface? Well, it turns out that in many remediation studies, it is important to know, in many remediation studies, in fact, microorganisms are injected into an aquifer to help with remediating, contaminants. And so it's important to know where these microorganisms are going in the subsurface. But to drive it home a little bit, looking at microbial enhanced oil recovery, in MEOR, as it is commonly called, microorganisms are injected into the reservoir with nutrients, and their metabolic byproducts mobilize residual oil, like in this particular example here. So geophysics can be used to monitor the transport of the microorganisms as well as their activity. So here's a recent paper that was published by Melage et al. In 2019. And so what we were trying to do in this particular experiment was to simulate microbial growth and to monitor its growth using electrical geophysical techniques. So in this experiment, the injection of lactates and nitrates is used to stimulate the growth of Shewinella ornidensis. And Shewinella is a common microorganism that is found in the subsurface. It's an iron-reducing bacteria, but it can also use oxygen and nitrate. So during the disseminatory nitrate reduction to form ammonium, Shewinella ornidensis oxidizes lactates to produce acetate, and nitrate is reduced to ammonium via nitrite, which is an intermediary product. However, nitrite, in fact, is toxic to Shewinella cells. And so what we see here in the bottom graph is the biomass, and this is the biomass that was measured in pink, the pink dots, and the black dots is the simulated biomass during the experiments. In green, the little green dots are actually the geophysical property measurements. In this case, we're looking at the electrical conductivity of the subsurface. And what you can see here really nicely is how the correspondence between the green dots and the pink dots and the simulated biomass, suggesting that the geophysical data is able the geophysical data parallels the biological measurements. So where we see a sudden drop in the microbial cell numbers, like within 150 hours into this experiment, and also after 350 hours, we see a corresponding drop in the geophysical property measurements. And when we look at the nitrite concentration, we see that these locations and these sudden drops in the microbial biomass actually corresponds to when nitrite was produced. And as already indicated, that nitrite, in fact, is toxic to the microbial cells. And so what we clearly demonstrated in this particular experiment is that the geophysical measurements cell density relationship can be used to estimate the cell abundance and can also tell us something about the metabolic state of the bacteria. Okay, let me see here. So in the next example here, we're looking at biofilms. As I've indicated previously, that one way in which microorganisms can change the subsurface physical properties is the growth of these biofilms. And that biofilms do in fact have, elastic properties and therefore can impact, seismic response. Now, biofilms are used for groundwater contaminated soil remediation, but they've also been suggested to be used as a sealant in reservoirs in which CO2 is being injected as part of carbon, capture and storage. And so the idea here is that the microorganisms, you can inject microorganisms into the reservoir, into the cap rocks, to help seal fractures or faults such that you prevent the CO2 from escaping, to the surface. So what I'd like to do now is to show you an example study that we conducted, and this is published in Davis et al. 2009, 2010. And here we used Pseudomonas aeruginosa is a model biofilm forming microorganism that's being used in the medical industry. And so we wanted to simulate the production of biofilms and to monitor that process using a seismic. And so in this particular experiment then, we did a 2D scan of the experimental column here. And what I show here is the amplitude of the P wave velocity, not the actual velocity themselves. And what we see, I've presented 5 different time periods. The first, the initial baseline measurements, and then the second day after the experiment, up to 29 days at the end of the experiment. And what you can clearly see here, again, we're presenting here the peak-to-peak amplitude of the seismic wave energy. And you can clearly see here a sudden drop after about 6 days into the experiment, a sudden drop in the amplitudes. And what we also observed is that the 2D scans obtained from the biostimulated column show that the transmitted compressional wave amplitude varied spatially within the scan region, with some areas exhibiting an increase of up to 45% change in the amplitude, whereas other areas showed a decrease of about 75 or 80% in the amplitude. But what was interesting about this experiment is that we saw minimal changes, less than 3% variations in the P wave velocity. So we conclude that the biofilms do in fact cause significant attenuation of the seismic wave energy. And at the end of the experiment, we destructive sampling were able to, with SEM imaging, was able to show regions where the biofilm occurred within the columns, and that we could explain the seismic changes due to a 4 to 5% biofilm saturation within the columns. And the next example, I'm not sure why my thing is going so slow. Let's see here. Oh my goodness, this happened to me before. Let's see here. Always does this. This is weird because this happened to me before. Let's see here. There we go. So here's an example where we look at imaging biofilms at a field site. Because the question is always, can we in fact upscale these laboratory experiments into field experiments? And what would that look like? So this is a site, it's a landfill site in Norman, Oklahoma. And we know that landfills, just like hydrocarbon contaminated environments, are bioreactors. And so we did some, we acquired some shear wave velocity, and we obtained the shear wave velocity by acquiring ground roll. We basically use the ground roll or the Rayleigh waves and inverted the Rayleigh waves into shear waves, as shown in this particular example here. And what we see is 3 distinct layers: the upper layer and a bottom layer that is bounded by a region of higher shear wave velocity. So here's a scale here, where the upper and bottom layer have a shear wave velocity approximately of 90 to 120 meters per second, whereas the middle layer has a shear wave velocity of greater than 150 meters per second. And so when we plotted the historical highest water level and lowest water level, we see that this zone of high shear wave velocities, in fact, bounds that higher water and lower water level for over a 30-year history. And so we retrieved some cores from the field site within this location here and did some SEM imaging to find out why we were observing this increase in shear wave velocity. And you can see here from the SEM imaging that in fact the sand grains are coated with the slime, and you can clearly see some of the slime extending into the pore structure and bridging two sand grains. And so what this demonstrates to us is that number one, the water table fluctuation zone is biogeochemically very active. In fact, the most biogeochemically active interface. And this biogeochemical activity results, enhanced biogeochemical activity actually results from the availability of electron donors and electron acceptors that stimulates the microbial activity. So what we conclude from this study and from the lab experiment is the fact that biofilms can be imaged by integrating both P wave velocity measurements and shear wave velocity measurements. In this case, we could sense the biofilms using P wave attenuation and using an increase in the shear wave velocity. In the next example, we look at biogenic gas production. Northern peatlands contribute to the global carbon cycle through the emission of biogenic production of CO2 and methane to the atmosphere by archaea or metallogenic microorganisms. So determining how much gas is present and where it is trapped in the subsurface is essential for understanding the global carbon cycle. The presence of gas that displaces the pore water in fact causes a significant change in the relative dielectric permittivity of the soil that makes ground penetrating radar an excellent technique for investigating this process. So in this example, published in 2011 by Perskian et al., they use ground penetrating radar to determine the distribution of biogenically produced free phase gas across the northern peatland. And so you can clearly see in this particular example here that we can see the distribution of the gas within the subsurface, not only the distribution, but also the gas content that is estimated from the ground penetrating radar. So this study really demonstrates that GPR imaging can be used to provide spatial information on microbial activity in the subsurface. So in the next example, I want to talk about the production of biogenic minerals or minerals that are produced by microorganisms. And as in the picture that I'm showing here on the right really shows that sometimes during remediation, it is important for us to determine where the biogeochemical hot zones are and to be able to capture these dynamic processes. So let me show you a few examples from actual field experiments. So in this particular example, it's published by Williams et al. In 2009 at the Rifle site in Colorado. It's a decommissioned vanadium and uranium processing facility with uranium contamination of the aquifer. Here, Williams et al., they use geophysical measurements to monitor the reductive immobilization of uranium-6 through the respiration of ion-reducing microorganisms, resulting in the co-precipitation of uranium-4 with iron sulfide. So on the left is a picture of the actual experiment, and the red line here shows not only shows the direction of the geophysical survey, and the top in the middle profile here they show the geophysical measurements before the experiment, and they show the geophysical measurements 3 weeks after the experiment started. And you can clearly see in the electrical measurement that there's a region here of changes, which is the biogeochemical, in fact, the biogeochemical reaction front. And on the right side, top right here, the picture shows a tubing here that was retrieved from the site, and you can see the blackened sands. And this blackened sands actually is the iron sulfide that has precipitated within these reaction zones. SEM imaging of some of the sands retrieved from this tubing also showed you can see the bacteria, and you can see associated precipitates, and EDS analysis suggested the presence of iron within the subsurface. And so here we see a really good example where the geophysics is used to capture the precipitation of conductive mineral phases.
Stella, if you could wrap up in 2 or 3 minutes, please.
Sure. And so in this particular example here, same thing again from the referral site. In this case, we're looking at the use of microbial-induced calcite precipitation, and it is used in engineering applications for stabilizing soils. And in this case, what happens is that the indigenous microorganisms are stimulated to produce microbial-induced calcite precipitation by stimulating urolytic microbes by injection of urea. And this clear example, again, you can see example locations where we see a reaction front where calcium carbonate has been precipitated within the aquifer. In this last example, just wanted to show you locations where, in this particular case, is from a hydrocarbon contaminated environment where magnetite is precipitated in the subsurface due to ion cycling. And we can clearly see again that, as previously shown, that the water table fluctuation zone is biogeochemically very reactive, and here we see magnetite has been precipitated. We monitored this site for about 4 years, and what was really interesting, we saw that the magnetite, or that the magnetic susceptibility response actually is transient and that it changes over time. And so the geophysics was able to capture this transient nature of the magnetic properties of the subsurface. And so I just want to leave you with some parting thoughts here about how geophysics can be used in order to advance studies. So for example, astrobiology, or used to search for life in extreme environments. As I've already said, that typically geophysics is used to look at internal structure, but we've never really used geophysics to image these microbial processes. And so I really believe that from some of the examples that exist in the literature today, that perhaps geophysics should be interfaced in some of the astrobiology studies to search for biosignatures on Mars, as well as even in the deep ocean basins, where we know there's a lot of microbial life that existed, but we do not know the nature of deep subsurface microbial life is poorly understood. Who are they? Who are the microorganisms? What are they doing? And how many of them are there? And I really believe that geophysical measurements can be interfaced with these studies to advance the search for life in extreme environments. And so this is the last slide here, just showing that we can also use it for resource exploration in terms of oil exploration. Oil seeps are associated with the presence of reservoirs at depth. And one technique that is used to locate oil seeps is microbial techniques, where basically a survey is set up and microorganisms basically samples are retrieved to determine the presence of microorganisms. And because I've already demonstrated that these microorganisms do in fact alter subsurface physical properties, that interfacing geophysical techniques with some of these microbial techniques can really advance investigations of oil reservoirs at depth. So just some takeaways here, that microorganisms do in fact leave signatures in their environment that can be measured by geophysical technologies. In fact, we have not developed any new techniques. We've used conventional techniques. And these geophysical tools can help identify biogeochemical reaction zones. They can help guide microbial and geochemical sampling. They can monitor remediation efforts and help resource exploration. And there's an exciting potential for using geophysics to investigate life in extreme environments. Thank you.
Thank you, Estella. That was fantastic. Okay, I think what we'll do is start with some questions for Estella, and then we'll open it up to everyone who is online and on the phone. I do want to make sure that those who are joining us just by phone feel comfortable asking questions as well. And I know there is one to start with after we get questions for Estella. Look at anybody. So Estella, I have one for you, and it's a spatial scale question.
Mm-hmm.
If you're looking for non-human mediated changes in biofilms and such in the subsurface, but where you're searching maybe in other planets or even a deep earth here for natural systems, would you anticipate the scale of the biofilms or the mineral precipitates or whatever technique you might be using that you would be able to detect these? Or is there a limitation of scale?
Okay, so it depends on, let's say on Earth, for example, the question that I typically always get is, what depths, can we, if we're imaging from the surface, can we really get to? I would say it depends on the resolution of the instruments that you're using. We do know that in geophysics, the deeper you go, and depending on the resolution of the instrument, you do lose resolution with depth. But you can get to that, you can overcome that challenge by doing downhole resistivity or borehole resistivity measurements, which again, you can also be limited, right? Because I mean, you can drill a hole that is 100 kilometers deep. And so, but that's what you can do. You can combine both the borehole measurements as well as surface measurements. Now, in terms of looking at, say, the signatures on other planets, geophysics always, I mean, we look at the contrast in physical properties between the target of our exploration and the surrounding area. So as long as there's that contrast in physical properties, then I'd say, yes, we can image it. But the challenge is whether or not can we distinguish between biotic or abiotic processes, which means that if iron sulfide is precipitated in the subsurface, it could come by just abiotic processes, right? It doesn't have to be biotic.
Right.
The geophysics right now, where we are in our understanding, we cannot tell the difference between biotic or abiotic. All we know is that there's a change. On Earth, we know that is microbially mediated because we're able to verify the presence of microorganisms in the subsurface in that interface. What we need to do, or where the studies are needed, is to search in our geophysical data if there are unique characteristics in our signals that we can attribute to microorganisms. Yes.
Great, thank you. Michael Manga, you had your hand up, but I see it's gone. I just want to make sure, did you still want to ask a question?
Yeah, let me just unmute myself. It takes a bit of time to get unmuted here. My question was whether there was any need to design new instrumentation or new instrumentation needs, because you're looking for processes that have not normally been the focus of geophysics. So I'm thinking about different energies or different frequencies.
I think for now, as I demonstrated that a lot of so for example, instead of using DC resistivity measurements, for example, we have been using complex resistivity measurements. And that's because the DC resistivity is not very diagnostic. All it tells us that there's been a change in pore fluid conductivity. It's dominated by electrolytic, conductivity. Whereas the complex resistivity measurements are much more diagnostic of surfaces or processes that are occurring at the interface, of surfaces. So for example, the interface between your sand grain and the pore fluid. And this is a technique that was developed in the mining industry. Induced polarization was developed in the mining industry for looking at disseminated mineral deposits, but we've been able to adapt it now for looking at, the microbial activity. So far we haven't seen a need for developing new instrumentation. Rather, the need is understanding the mechanistic, the mechanisms by which the microorganisms causes changes in the geophysical, properties. As well as revising most of our models, geophysical models today don't take into consideration the biological component. So there is also a need to advance this modeling to incorporate biological, processes.
Great, thank you. I think what we'll do, there'll have to be 6-7 minutes before we, Elizabeth and I, thank everyone and wrap up, is open the questions up broadly to any of the speakers. And I would like to start with if Ben Phillips from NASA is still with us by phone. I know he had a question from Michael. I cannot tell whether he's still online.
I'm here. Can you hear me?
Yep. Perfect. Yep.
Great. Thanks so much. Michael, thanks a lot for your talk. It's very interesting and great to see some of the priorities identified in the erupt report, getting attacked here. So you know that the inventory of submarine eruptions, past and future, are something that can be addressed through looking at the satellite record, certainly for observations of pumice rafts like you spoke about, but there are probably also other opportunities in looking for particulates and ocean color variations, looking directly at erupted plumes that breach the ocean surface, ash and SO2. And I'm wondering if you have any thoughts on using those other types of observations to constrain the kinds of models that you're working on, and further work from both directions, from the observational record and with modeling to better understand this part of the volcanic system and improve that global inventory.
Yeah, excellent, Ben. That's a great question. So let me first start by pointing out that the existing network of satellites has been phenomenal to track these rafts, especially when we know the eruption has happened and roughly where it's going. So the example I showed you earlier, those were images based on MODIS, Terra and Aqua, Sentinel-1, 2, and 3, and Landsat-8. So we have had 3 different students work on trying to look for rafts more generally using machine learning, because when we have these well-characterized rafts, we can identify signatures of them, and then we can go back through the historical satellite data. It's quite challenging because rafts and clouds can look quite similar, so can some algal blooms. There can also be plankton blooms fertilized by the raft as well. So our results so far have been mixed, but it's not something we're giving up on.
Great. Would anybody else? I don't see any hands raised or any messages in the chat room. Would anybody on the phone have any questions? And online? Check one more quick time. Scott, it sounds like you have a question for Michael and for Bill.
Hang on. Oh, yeah. Hi. Yeah, I think Bill answered my touched on the question I think I had about Long Valley. But Michael, I really enjoyed your talk, and there was an image early on that showed the feature in the Tonga Kermadec area, the Hav volcano. It sure looked like the dome was sitting on top of some much larger feature, sort of looked caldera-like in a bit to me. Reminded me of Mount St. Helens after the original blast. Is there history there of an earlier explosive eruption?
Yeah, interesting. So the size of the caldera at the Havre volcano is roughly the same size as Crater Lake. It's about 4 to 5 kilometers across, depth of 700 meters. And so it was produced by a caldera-forming eruption. And the deposits from these caldera-forming eruptions create these big fields of sediment waves around the flanks of the volcano. In the Kermadec Arc, there are a number of these submarine volcanoes that have calderas. Healy, Macaulay, or 2 others. And these caldera-forming eruptions probably erupted many tens of cubic kilometers of magma. So an order of magnitude or more bigger than the 2012 eruption.
Great.
Great, thank you.
Okay. I think we'll take the last minute to wrap up. I just want to say thank you again to our speakers. I very much enjoyed this, and I have to say I very much appreciated the opportunity to gain a deeper perspective into what some of my board colleagues do when they're not sitting around the board or on our monthly telephone calls. And I hope we can find other opportunities to do this, to hear from all the others as well. So on that note, I'm going to hand it back over to Elizabeth to do the official wrap up. And I know we'll see some of you, well, certainly the board members, and we'll see some of the rest of you tomorrow morning as well. Elizabeth.
Thank you very much, Isabel. I'll just echo Isabel's point, and first thanking our speakers for the excellent talks. This was really a lot of fun. Different topics, different mechanisms, tools, models, looking at things at many different scales, but yet with some connections throughout all of them to one another. So that this was really enjoyable, and thank you so much for agreeing to do this. I wanted to thank our audience as well for participating with us today. This slightly revised version of our spring meeting of the board, and to thank the staff team again for all of their efforts, Deb, Eric, and Courtney. We will be posting the recording of this, as I mentioned earlier, in 7 to 10 days on the website. We'll let all of you know when that is posted. And if you haven't signed up for the BESR listserv to be notified of future meetings and so on, when you registered for the meeting and would like to, please feel free to reach out to me, eeide@nas.edu, and we'll be able to get you hooked up so that you can be on the list for receiving future announcements of our activities. And with that, I will say thanks for us for today. Look forward to seeing the BESR members tomorrow at our executive session, as well as the sponsors of the board. Thanks everyone for a terrific morning or afternoon, depending on which time zone you're in. Take care, everyone. Please be safe. Take care of yourselves. All right. Bye-bye.